And welcome. I'm going to be covering Quartus Prime 19.1 in this video. And so for some of you, this will be a refresher on how to use it. I've also got another video called the first Quartus program video, something like that. That's in the YouTube playlist. So this I'm just doing as an addendum, just walking through a program, how I would do it from front to back. It might be a little bit different than my initial tries at using 19.1, and I left in all of the errors in those videos so that you would have a good representation of what I went through and some of the things that you might go through when you first install it. So this video is more geared for now you've used Quartus a few times, you've got it underway, and so let's go ahead and walk through all the functions again and see how smoothly it should operate. Okay, so I've already got Quartus pulled up, and I always start a new project wizard unless I'm opening a previous project. And you have to, if you're going to open a previous project, you have to get to where you store them. For me, it's in C here, and you have to make sure you open the QPF. Okay, that's the Quartus project file. So if you just open a BDF, it will only open that file. It will not open everything else with it, and you cannot run any simulations, and you cannot compile. If you want the whole thing, you have to open the Quartus project file for that project. Okay? So just want to make sure I'm coming through. I'm good. I'm going to go ahead and start the new project wizard. So the very first thing it's going to ask me is, where do I want to store this? And if you have watched the other videos already, you'll know that the default location is this Intel FPGA Lite 19.1. For whatever reason, when I initially installed this, I somehow, because even though I'm the administrator and the manager of this computer that I'm using, it would not let me read and write to this location. I could create things there, but then I couldn't go back in then and save. And so, if I tried to open a project again, it said I had no access. And so what I've done is, instead of using that default, I created my own folder right underneath C. And I know you're really not supposed to do that, but I did it anyway. I'm not that worried about it. You could bury it in a few folders if you'd like, but you want to get a folder that's specific to this class. And so I just called mine EECT122 Quartus. Right? Now, inside that main folder that you're going to use for the class, you should set up a new folder for every single new circuit that you build. You don't want to just keep going in and editing the same one. You want to keep these separate. So like I'm going to create a new folder called, what should I call it? Quartus Intro or something like that. Doesn't matter. Doesn't matter for this because I'm not, creating a lab 1 or a lab 2 or a lab 7 or whatever. So just say Quartus Intro. So I'm going to select that one. And so now everything is going to be stored specifically into this folder. All right? I don't want to just smash everything together here. If what happens is you'll have a bunch of files named waveform.vwf, because that's what you have to call all of your vector waveform files. And you'll have all of that stuff kind of crammed in the same place. And it's hard to get to the actual lab that you want to get to. And Quartus, when it looks back into this folder and it goes to run the vector waveform file, sometimes it'll run a different project altogether. So if you have everything quartered off and you have everything in the same place in its own specific folder, Quartus won't have any issue with it. So there's my folder. Now I have to name it something. Just for this exercise, I'm going to call it Quartus Intro. No spaces. Don't start it with a name. I don't know if they allow you to start it with a number, like if you did 122 Quartus or something like that. Just play nice with all the names because it is very particular in how things operate. I don't even think you can. Yeah, I'm pushing the space bar right now. It's not even letting me input that. So just choose something that doesn't have any spaces and try to stay away from characters. You can put numbers at the end. I know you're good to do that. I just don't know if you can put them out in front. So just play nice with it, okay? So I'm going to go ahead and click Next and make sure this is at empty project. Do not use a template. The next one, we are not to a spot where we are going to be adding anything yet, and I don't even know if we will, unless I'm trying to help somebody through something. The next one, however, you do need, all right? And this is what, page 3 of 5 or whatever in this little wizard that we're doing. So the only type of device that I have loaded is the Max 10 devices. And I told you in the install video, if you just wanted to download all the packages and you had the space, go right ahead. If you did that, then you're going to have a list. You're going to have like the Cyclone 2 and the Cyclone 4 and the Cyclone, I think there's a Cyclone 5 now, and you'd have all of those other families. So for those who just downloaded Max 10, we don't really have to choose anything there. But for the device, I'll go ahead and dial down to the Max 10 DA because that's what we have. So there are different series of the Max 10 even, but the one that you got for this class through Jurassic, the DE10 Lite, is a Max 10 DA. So once you have that selected, I bring my cursor down here on this line and I just roll my mouse scroll. My mouse has a scroll in the middle. Okay, and I'm just scrolling down. I'm looking for 10M 50DAF 484C7. And there it is. 10M 5DAF 484C7. So I select that, hit next. Okay, now this is something I also skipped in my initial video, is I didn't go ahead and plug in the simulation here. You might as well go ahead and do it at this point. Because you're going to have to do it at some point anyway. So instead of having to go back through the options, just go ahead and click Simulation and Model Sim Altera. Okay, so now I'm going to go ahead and click Next and Finish. So now this is going to create the environment, and if you're running it for the first time, the 19.1, this is where you would have gotten stopped if you were not allowed to write to that folder. And that's why it hung up on me and froze and crashed. So because I can now write to the folder I'm saving this project in, I don't have any issues. All right, so you may remember the next thing that we want to do is create a block diagram file, a BDF, and that's about the third or fourth one down here. So I create a BDF. Now the very first thing I do is I change this because you may have seen on the very first screen, I didn't point it out, but if you go back and watch that part, you'll see it says that the entity has to be named the exact same thing as the project. And so you also want to call your BDF the exact same thing as whatever your entity is called here. So Quartus intro with the capital Q and the capital I. It is case sensitive. Now here's the nice thing about Quartus. It knows that it has to be named that, and so when you go to File, Save As, it automatically names it what it's supposed to be named. Don't adjust that or change it. Leave it alone and just say Save. Now that I have a name on this, I feel better about adding components. I like to have that squared away before I get started. Okay, 2 ways that you can add components. One way is through this little AND gate right here, and that is called the symbol tool, and that brings up the symbol tool interface. The other way to do it, the quicker way to do it, and a student actually showed me this a few years ago. I went 15 years without knowing how to do this. If you just double left click on the schematic itself, it'll bring up the same symbol tool. So that's kind of a neat little thing somebody stumbled on. And in terms of how all of this stuff is structured, if you knew where everything was here, you could go find where all of the stuff is, all right? I don't like doing that. I like to just go to the search bar here, except this is not a predictive text search. This is not like Google where it says, oh, you want to go here, and tries to fill in what you're trying to type. This is a stubborn search feature. In other words, you have to type in exactly what the gate is called, or it's not going to show you anything. So, for example, if I wanted a 2-input AND gate, and I just type AND, okay, it gives me nothing back. It says I have no idea what an AND is. But the way that you name a gate in Quartus is the name of the gate, the type of gate, and or whatever, and then the number that follows it is how many inputs there are. So for a 2-input AND gate, it would be an AND 2. Now, it sees that and goes, oh, okay, I know what you're talking about. That's an AND 2. And if I scroll down here, I can see all the different, I can do up to a 12-input AND gate if I wanted to, something ridiculous. So if I just wanted to put an AND 2 in here, and then here's the other gates. Excuse me. Those are binary operations. So the NAND, you can do up to a 12 input NAND gate. You can do NOR gates, right? And ORs, different types of ORs. Now, the exclusive NOR and the exclusive OR, they are not there. The only way the function works is if there's two inputs. So there isn't a crazy schematic for the exclusive OR and the exclusive NOR. But those are all of the basic gates, the 5 basic gates and then the 2 exclusive gates. Okay, they're all in this same folder. But like I said, I don't try to dial down in and use that. It's easier to just type in what you want, X OR. There you go. Okay, but just you have to know what the actual gate is named and have the exact, it's not going to show up if you just type it in. You have to have the exact name of the gate. Okay, so I'm just going to do an and 2 and place it on my schematic, and I'm going to zoom. So I'm going to hold the control key and I'm going to roll my mouse to the front, so that way I can zoom in on the schematic itself to make it a little bit easier to see. So now I need 2 inputs here. So double click, and you have to spell the word INPUT. There it is. Now if I have to add more than one of something, what I do is I put this on here, and while it's still selected, hit Control C, click right below it, and then Control V. Okay. The other nice thing about Quartus is everything lines up nice and neat. So if you stack your inputs on top of each other, you can see that it directly lines up with the inputs of this gate. Okay. Now here's one thing that you can do, which I don't like to do, but you could if you wanted to. And that's the easiest way to wire this up, is to click the device here and hold it, or click the gate, pull it over to where it just kisses the edge of those inputs, and then pull it back. So like, oh, it didn't do it. Try it again. Well, oh, you have to leave it. That's what it is. You have to click and let it sit there, and then you can pull it back. That's what it is. So it's like, I want this to be connected here, and then I can pull back and it'll automatically wire it. I don't like doing that. I don't know why. They do it so it makes it easier, but I am just, I guess I'm set in my ways. I like to go find the crosshair, click, pull, let go. So you have to click and drag, and then you let go when you see the other the other box that you can connect to. But if you want to do the fast way, that's fine too. All right, now we need an output. So I'm going to double click, OUT, PUT. I know it's right below the input, but I still type it out. There we go. And so same thing. I could move this over here, let it go, pull it back, and now they're wired. I guess I'll leave that. Okay, so everything looks good so far. I've got 2 inputs. I've got an output, and I can watch how this thing functions. So I could leave these named Pin 1, Pin 2, Pin 3, but I'm going to name them something much better and say A, B. If you ever have me for C programming, this is a no-no. I will never let you have single letter variables, but for digital inputs and outputs, I think it makes sense because especially with our discussion from, you remember from 112 when we talked about Boolean algebra and De Morgan's, right? Those fun topics that everybody loves. I love them, but not everybody loves them. But we use single variables like that, so I think that's why it makes sense to do it in digital here. Okay, so there I've got my inputs and my outputs named the way that I want them. I'm going to go ahead and see if I have any syntax errors now. In other words, if I have any connections that aren't made correctly, or maybe I have 2 inputs that are connected to each other or something like that. Those are the kind of errors that the compiler checks for. So when I'm ready to compile, I come up here to the blue play button. That's what I call it because it looks like a play button. And it's actually the start compilation. The shortcut for that is Control L. This is one program I never use the keyboard shortcuts for whatever reason, but I guess I'll just go ahead and hit the compile. It's been modified. I want to save. Yes, I do. And now over here on the left is where you watch to see how your progress is working. For whatever reason, the very first time that you simulate your BDF is when it takes the longest in this analysis and synthesis, so it's going to sit here for a second before it moves on. Subsequent compilations of the same BDF will be much quicker. So it's almost like it makes it loads it with data, and then if any of that data changes, that's what it does in the next compilation. I'm not sure. But anyway, we got to wait for this thing to go all the way down to the EDA netlist writer. The EDA netlist writer is what compiles something together to be able to send it to the vector waveform file. And if you do have an error, it's going to happen in the analysis and synthesis. So that's where you'll throw like any of your syntax errors. All this other stuff is going to run. You just need to let it run and do what it's going to do. So the analysis and synthesis is the most important part, at least for what we do. So this is good. We have green check marks. We want all green check marks. A lot of dead air. I don't like dead air in these videos, but my computer sounds like it's about to take off right now into outer space because the fan's working overdrive. So this program really lags down the processor. Okay, there we go. So now you can see here, you may remember that we've got 14 warnings. Now the warnings are, you didn't tie this thing to ground, or what are you going to do when you actually build this? Those are the kind of warnings that are happening. What we are concerned about is the errors. And so as long as you don't have any errors, then you can go ahead and move forward. But if you have any errors, you have to fix those, whatever it is. Okay, so we're good here. I'm going to go ahead and close out of that. I am now ready to simulate my design and see how it operates in a vector waveform file. So I'm going to go ahead and click the new file icon, and about 3/4 of the way down, you see the University Program VWF, Vector Waveform File. Go ahead and create one of those. And just like I do with the BDF, the first thing I do is come up here and say File, Save As. Don't change it from waveform.vwf. The simulation is set up to where it's looking for the file named this. So just leave it alone and let it be called capital waveform.vwf. That was another error that I kept having. So leave that alone. I'm going to click Save. All right. So now over here, you want to right-click anywhere in the white, and you want to say Insert Node or Bus. Okay, and then you come over here. You could do them individually. I always like to do them all at once, so I go to my node finder. Now notice it's not populated, but you have to have the filter set to pins all, and then you want to list all the pins in your schematic. And so for us, we just have an A, a B, and an X. So you can select and do them individually, or you can just hit the double arrow and bring them all over. Say OK and OK. Okay, now we have them on our timing analysis vector waveform file. So what we want to do is we want to give a signal for the inputs, but leave the output alone. Don't change the output. The reason why you see the hash marks here is because this is an output. We don't know what the output's going to be. The whole point of this is that we're going to put some different inputs through that gate and then see how it changes the output. So we are not assigning a signal to the output at all. We want to leave the hash marks. But for the inputs, we want to, since there's 2 inputs here, we want to accomplish a couple things. We want to make sure that we get through all of the different input combinations there are, which with 2, there's 0, 0, 0, 1, 1, 0, 1, 1. The easiest way to accomplish that is to set one of these at a certain frequency and the other one set for double that frequency, okay, or half that frequency, I should say, double the period. All right, so there are 2 ways to create these signals. One way is to use this little watch. It's called the Overwrite Clock. And so here what you would do is you would put in the actual period. So how long do you want this, do you want it to go for 100 nanoseconds, and that way you have a transition at the 50, 50% duty cycle. You can really fine-tune your clock there, all right? Typically what I do, because it's a little bit quicker, and all I really care about is just giving myself some transitions here, I will come up here and do count value, and then just say how often do I want the signal to switch. And so my transition is going to occur every 50 nanoseconds. That's usually what I start off with 50 nanoseconds. There you go. Gives me a nice square wave, and it transitions every 50 nano. Now, the other thing I don't like about the default here is that you see my hash marks happen every 10 nanoseconds. I want the hash marks to be wherever I have this very first signal. Okay, so I'm going to come up here and say edit grid size. I want the grids every 50 nano. So there we go. So now it better lines up with the two signals I have and makes everything a little bit more readable. Okay, so I said the second one, to account for all the possible combinations, should be double the period of what I just did. So that also means I now, instead of transitioning every 50 nano, I want to transition every 100. So I select this, count value, now I do 100. And if I had two more inputs here, the next one will be 200, the next one will be 400. You just keep doubling it each time. So here's how that works. If we look at this as a graph of amplitude versus time horizontally, if I drag my cursor to any point in time, the question we're asking is, if I, like this very first point in time here, if I put that A at that point and that B at that point through that AND gate, what happens to the output? Well, we know that an AND gate has to have a high before the output is high. So I'm predicting that this very first section right here is going to be low. The next section over, we have a 0, 1, which through an AND gate is still a low. So low, low is what I expect. The third one over here, I have a low, high, which is still a low through an AND gate. So I think the first three sections are going to be low. However, now we've gotten to the point where we have a high, high. Right? And so now I expect the output to transition to high. So this is the output I expect if you follow my cursor. Low, 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 high. And then you see the way that we have this set up, it repeats 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1. So it just repeats over and over and over. So the output will repeat over and over as well. We should get low, 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 high, and then low, 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 high, over and over and over. Okay, so we are ready now to go ahead and simulate. And I'm going to do the timing simulation. This is the functional, just to see, if we, what happens without considering propagation delay and things like that. The timing simulation actually takes that stuff into account. So go ahead and run the timing simulation. Yes, it's changed. I want to save my changes. Right now it's working my processor, and there we go. Okay, so it did what I expected it to do, right? It went low, 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 high, low, 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 high. So when you turn, when I say I want to see the output waveform of the vector waveform simulation file, this is what I'm talking about right here. And if you want to grab a copy of that, one way to do it is do an alt print screen. So it makes a copy of just this window. The other way to do it is to start your snip. I use the snip and sketch. That's the new one that replaced the snipping tool. And then you can just say new, and then just grab a screenshot of this. Okay, and then it gives you the option to save as a picture. Okay, so that's one way to do it. The other way is to do like an alt print screen, and then start Microsoft Paint, and then you can come in here and do a Control V, and then it'll save it here, and then you can do a file save as, and save that as a picture as well. Okay. In terms of the BDF, because I can't open a BDF in Canvas, same thing. I would just do either a alt print screen, or I would do a snip and sketch of the. You might go ahead and include everything here. Okay. Or you could, like I said, you could just do in this case, if you have it full screen, you could just do a full print screen. So alt print screen just takes whatever window is out in front. So like in this case, if I did a full print screen, it would take everything and it would put this on top of it. If I do an alt print screen, it just captures this window here, whatever window is on top. Okay, So let me come back. And the next thing I want to do is I want to go ahead now and download to the board. So I got rid of my vector waveform file. I'm comfortable that this is working. Now I want to put it into a real world scenario. So the first thing we need to do is we need to go to Quartus, and we need to go find the De10 Pin Assignment. And I can do that back here. I believe I said it was the very, very first one, right? Maybe? There's the DE1 Cyclone 2. Did I not put it up? Did I say I was going to put it up? I think I did say I was going to put it up. Well, I know where it's at, so I'm going to go pull it open real quick. It's actually in the 112 as well. So what I did is I went into the DE10 Lite. I went into the DE10 Lite manual, and I pulled out the most important parts for what we're doing, at least. And this should be an announcement in Canvas. And so I pulled out, this is kind of like the DE1 board, where I've got all the slide switches and all of their addresses, all of the LEDs and all of their addresses, and then ours have 6 7-segment displays, and so that's all of their addresses as well. The 2 debounce push buttons that are right here, I included those addresses, and then there are internal clock signals that, with your knowledge of Chapter 12, you could knock those down to something useful and then use them in your circuits. Okay, but those are pins that you can attach to for like a clock pulse. But 10 meg is pretty quick, 50 meg is pretty quick. You'd have to use some asynchronous counters, some modulus counters to knock those down. Okay. So I just need 2 inputs. I'm going to use C10 and C11. Those are my very first 2 switches on my board. Okay, so I'm going to go back to Quartus, and I'm going to go up to Assignments, Pin Planner. And there's a list of my inputs and outputs, and so one of my switches is going to be C10. Now, instead of saying pin underscore C10 or whatever the full name is, all you have to do is type in the pin number. So C10, enter. The next one, C11, enter. Go back to my document here. Not this document, but the other document. And now I want an output. I'm just going to use the very first LED, and that one is A8. So I go back to my pin planner, and now I just type in A8. Now, sometimes this little scroll bar gets thrown off to the right here, and you try to put your location in here or somewhere. Make sure that this is all the way over to the left when you're doing this, and that you're putting in this location. Otherwise, it's going to throw an error over here because it looks very similar. Okay, so I've got all 3 in, and this is always a question: is now that I have my pins assigned, do I go ahead and save from here? No. All you want to do is just go ahead and click out of that, because you can see, if I scroll back there, that it has now assigned those addresses. But here's the thing: it has not locked them in so that you can send it to the board. So you notice over here on the left, now you've got some stuff that is question marked. So you've made a change and have not compiled it since you've made those changes. So we want to go ahead and lock this in and come up here and hit the play button once again. And we have to go through the same setup here, and it'll compile it, make sure there's no errors, make sure that the places I wrote to are places I can write to for what I'm trying to do. Then I can go ahead and download it to the board. So just a little bit quicker this time, at least to the analysis part, and the rest of it should follow suit. Again, you're not looking for 0 warnings here, you're looking for 0 errors. You can have as many warnings as you want, presumably. And finally, the EDA netlist. Okay, no problems. We are good to go to send this to the board. Okay, now, one way to do it is come up here to the tools and come down here to programmer. I like to just use the little icon up here. It's the third one over. and it says programmer. I always think it's the little diagram that looks like it has a piece of bacon frying in it, and so that's how I remember or distinguish it from the other ones. It really doesn't look like a piece of bacon anymore, but in version 9.1 it sure did, and so I've just kept that. So anyway, go ahead and click the programmer. This is setting up the interface between the actual physical device and your project. So there's my device. I don't have to touch anything here. The only thing I might have to do is the hardware setup. You may have yours set to no hardware. Okay, now here's the other thing, and I'm going to put the camera on for just a second. You have to have your, sorry for the laptop camera, it's so shaky. You have to have your board turned on and plugged in before, and I've actually got a program running on it, so I'm actually going to shut it off real quick and then turn it back on because it had a program running from yesterday. So essentially, you know, if you've just plugged it in, your board should be doing this in the demo mode. That way, it can load the USB blaster that's going to be used to turn this thing on. Okay? So let me get back to my desktop here and get rid of this for just a second. So I want to make sure that I'm choosing, now that I have it plugged in, I want the USB blaster. Okay? Now I'm going to go ahead and hit start. And you'll know that it sent it to your board correctly if it looks like this. Okay, now notice, you know, we wrote to the very first LED on there, and we're using the very first two selector switches. And you can see there it's actually calling it LED R0 and switch 0, switch 1, switch 2. Alright, so right now, remember, I'm running an AND gate, and both of those selector switches are low. Okay, I'm trying to stop moving my hand here. But anyway, I'm going to run through the different possibilities. We already see what happens with 0, 0. Here is 1, 0. And then I'm going to do, there's 0, 1, still nothing. But then when I do both of them high, that LED turns on. Now you'll notice that the other ones are in kind of like almost a floating condition where they're illuminated, but I wouldn't consider those to be high. If that's distracting, you could, in your BDF file, you could go ahead and just tie all of those low so they all turn off if you wanted. Okay? But anyway, looks like it's working. Okay? Download it to the board. 0, 1 doesn't work. 1, 0 doesn't work. But 1, 1 does turn it on. Okay? So that's the operation for everything that you're going to do. And, you know, even with circuits that are more difficult than that, you just have to make sure that your BDF file is correct, that you have no syntax errors, that you have everything connected that you want connected properly, and that you haven't missed anything or, you know, accidentally connect a wire that shouldn't be connected. You have to check all of that stuff and troubleshoot it before you can even think about either simulating it in a vector waveform file or actually, you know, sending it to the board and prototyping it. And using the actual physical switches and the actual LEDs. So anyway, that's just a quick run through of this. The next thing I want to do is to get rid of that. And so I'm going to be referencing what you might see on the Lab 3 for 222. And I'm going to leave these switches where they're at for now. And I'm going to leave this output over here. And I'm going to go ahead and add a JK flip-flop. JKFF, just a generic one here. All right. Now, I want to leave this in toggle mode. And I just want to, you know, just to show how it operates. And so what I'm going to do is I'm going to tie J and K both high. And I'm also going to tie the clear and the preset high. Actually, I'm not going to do that with the reset here. I'm actually going to put an input on that so that I can initially clear it with the vector waveform. But I'm going to tie the preset high, and I'm going to tie J and K high. The way that we do that in Quartus is we attach to what we call VCC. And if you just type in VCC, it brings up this little, looks like a 90-degree T. And that's essentially 5 volts. Okay, so I'm going to tie this high because I don't want to use it. So click, pull, drag, let go, click on that little node, and then come up. And then same thing. I'm going to connect K, and I'm going to connect J. So I've tied all three of those high to put it into toggle mode. Now I do want to have an input on the clear here, so I'm going to go ahead and rename this one as my reset instead of B. Okay, and notice how it takes away that pin assignment. So I'm going to go ahead and connect this to here. Okay, my output I'm going to leave here, and I'm going to go ahead and call this Q instead of X because that represents better what it actually is doing. And so I'm going to have to reassign those pins, no big deal. And same thing here, I'm going to call this my clock pulse. Okay. Now, to make it negative edge triggered, I want to go ahead and put a NOT gate out in front here because notice it's positive edge triggered as a default. So I'm going to double click, and the NOT gate is actually spelled in OT. It's not inverter or INV or something like that. It is in OT. So I'm going to go ahead and put this in here. Now I'm going to connect, click, drag, let go, click, drag, let go. And make sure you saw what happened there. If I do a Control Z, if I click and drag, it'll throw up a box like, "Oh, do you want to do something right here?" And I say, "No, keep going." Okay? With the previous versions of Quartus, if you didn't do that transition fast enough, it would connect in both places. But it seems like this version has gotten rid of that. So it's very hard to misconnect. So anyway, there we go. I've made a connection now. I actually made it too long. There we go. Now I have a negative edge trigger JK flip-flop that's wired to be in toggle mode that I can manually reset with my vector waveform file. Okay? So I think I'm ready to compile at this point. Let's go. Yes, I want to save my changes. And we'll let this compile, and then we'll go see what it looks like in a vector waveform file. And I'm probably just going to use the one I used before, but I'm going to have to do some work to it. Oh, doesn't like something I did. What doesn't it like? Let's see here. I'm glad this happened. Okay, so I'm going to scroll up here to my errors. Can't elaborate top levels. Oh, okay. I'm glad this happened. So glad this happened. So you can see here it says logic function of type not and instance inst is already defined as a signal name or another logic function. This is a glitch with Quartus that did not used to exist. It only exists in 13 and higher from what I have seen. So every time you add a symbol on here, Quartus doesn't distinguish between them. They're all just symbols. Okay? Now notice what happens. This is named INST. This symbol is named INST as well. So it's not that I have something connected wrong. It's the fact that when I added these, for whatever reason, it didn't call one of them INST and then the next one INST1, because if I were to do another NOT gate, that's exactly what would happen. So if I click and I add it, oh, there you go. See, it has the same glitch. It should not be doing that. It should be saying that that is INST2 at this point. Okay? So anyway, I just have to come in here and I have to rename one of the two. No big deal. So I select it, right-click, Properties, and that one's now Inst1. Oh, there's something else. Okay, how about 155? There we go. That's Inst 155 now. Now let's see. This is I don't see another INST1, but that's okay. It says that it exists, and so I believe it. So I'm going to come up here and compile this again. And hopefully this time we don't have any errors. But I am glad because that is going to happen to somebody, and I always have to answer that question, so I'm glad it happened in this video. There we go. So it looks like we're going to get a clean bill of health this time. right. So maybe if you have a faster computer than I do, that it works quicker, or maybe there's some other setting you could use to make this process quicker, but mine is going super slow. Okay, there we go. So we've got that completed now. I am ready to go try this out on the vector waveform file. So I'm actually going to open the previous one that I just had. And so Quartus intro, and I don't want to look at the design files. I want all files. And so here it is. There's my vector waveform. Okay, now I want to get rid of all three of these. So I select them all and just delete, and then right click again, insert node or bus, node finder, list. There's my new inputs and outputs. Pull them over. Okay. Now my reset, I told you I was going to show you how to do a force high. So I want my reset to be high at all times, at least for now. So I'm going to go ahead and put that at a 1, and so you use this one right here, the third one over. It says force high, and so it makes it high for the whole time. If you wanted the opposite, if you wanted it low the whole time, guaranteed, then you could just come up here and hit the low. So it defaults as a low all the time, as I said, as a default. So the reset I am going to make high. However, if this flip-flop does not have an initial value, it doesn't know what value to toggle to next. So I'm actually going to just put a little initial asynchronous reset in there so that my flip-flop has an initial Q value of 0. I could do the same thing with the set if I wanted to. I just chose to do it with the reset. So I'm going to make this one little section here, and this is the other reason I changed the grid size, because this goes by grid size. I can only do a 50 nanosecond section. If you want a smaller section, then you have to change your grid size. So I'm going to take that one little section that I have selected here and force that low so that I have an initial asynchronous reset, and then it doesn't affect the circuit the rest of the time. But it gives Q an initial value here. Otherwise, it's going to leave all hash marks on the output. So my clock pulse, I'm going to have this go every 100 nanoseconds, just so I can see this thing toggle back and forth. So I go to my count value. I want to transition every 100. That gives the reset enough time to get back to 1. And there we go. Okay, I'm actually going to move the order around here. I'm going to move the reset up so that it looks like this. And I'm actually going to do this, put the reset on top. So that way the clock pulse is still next to the output here. All right, I'm ready to simulate. So here we go. Do I want to save the changes? Yes. And there we go. So we see that this asynchronous reset gave the flip-flop an initial Q value of low. And then remember, this is a negative edge trigger the way that I have it set up, right? I put a NOT gate into that triangle. So when the clock pulse goes from high to low, that's when the output changes. And again, so we have to wait till it gets to the output high, and then the output changes from high to low, and we get another transition. So you can see, and this validates what I said about the frequency. This frequency has a period of 200 nanoseconds. This one has a frequency that's half that, right? The period is twice as long to complete one cycle. You can get 2 cycles in the amount of time you can get 1 cycle of Q. So that's why we say that the output Q is half the frequency of whatever the clock pulse frequency is. Or the other way to say that is the clock pulse, the output period is twice of that of the clock pulse. Okay, so either way you say that, it's valid. Okay, I think that's enough for this session. If you wanted to, you could connect the clock pulse to one of those pins on the board and then use an asynchronous reset on your actual physical proto board and download it and then see how Q changes on the LED. The problem is that clock pulses is super, super quick. So until we talk about Chapter 12 where we do the modulus, which if you go back and look at your 112 notes, you should know how to do that, you could knock that 50 megahertz down to something more reasonable to where you could see the LED flicker on and off if you wanted to, okay? Otherwise, you'd actually have to attach some actual, clock pulse to the inputs. Which, if you have something that can do that, if you have a function generator, you could do it. If you have make sure it's at TTL levels though. If it's too high, you'll burn out the input and damage the board. So anyway, that is the end of this discussion as your reintroduction for some of you, and for some of you just a reinstatement of what you already know on how to use Quartus and how to download to the board. Thanks for watching.